when Albert Einstein in 1915 basically had finished the theory of general relativity, which is sort of a modern theory of gravity. And as part of that development, he predicted that the movement of bodies would create gravitational waves. And it's rather similar to when you throw a rock into a pond and you see the ripples. But we now believe that our physics takes place in the combined space-time continuum. We call it simply space-time. Astronomers have known for a long time that when stars are born, they quite often are born in binary systems and even higher order triple systems. But a binary system evolves in time. And if it's two stars like the sun, not much happens in the life of the universe. But if the stars are massive, they can explode. And when they explode as what we know as a supernova, they leave behind a very compact object, either a black hole or a neutron star. And these objects have masses that are similar to the mass of the sun, but their size is basically the size of Clemson. And in these binary systems, it can happen that both stars are massive and both leave behind a black hole or a neutron star, and that the binary system survives all of these explosive events, and it remains a binary. And so then you have two black holes, for example, that are orbiting each other. And then Einstein kicks in. He said, if that happens, it loses energy by emission of gravitational waves. It shakes space-time, and in doing so, it loses energy. That makes the binary get even closer together. It radiates even more strongly. If it's two black holes, you make just a bigger black hole out of it. And if it's two neutron stars, for example, then you create a new black hole. But the process of taking two neutron stars and shredding them apart creates what astronomers call an accretion disk, which doesn't last very long, fractions of a second perhaps. This neutron star material, that accretes into the new black hole, but it is very hot and it can radiate. In 1975, we discovered a binary neutron star system where both were so-called pulsars. They make radio emission that is pulse, at least it looks pulse from our perspective. And both of them were pulsars. And pulsar is radio astronomy, which can very precisely measure that binary system because we had two pulsars beaming at us. And so we looked at what happened to that binary system, and sure enough, it changed its period exactly as Einstein had predicted. So we have known now for quite some time that gravitational waves really do exist and that they behave sort of according to Einstein's theory. What we have not been able to do until very recently was a direct detection of gravitational waves, not an indirect inference that, okay, they must possibly, it looks like consistent with. No, none of these words, but a direct detection.